Okay, so it's my great pleasure to introduce Ronan Fablet. So Ronan has been has an engineer degree in space and aeronautics, and a master degree in applied uh, math. And he did his PhD in computer vision at the University of Rennes. He then moved to Brown University in the US, where he worked as a postdoc. And then he returned to France to work as a research scientist for the Department of Fishery Science and Technology in Brest. And then he stayed in Brest and has been a professor at IMT Atlantique since 2008. And his main interests include signal processing and computer vision and applications to ocean remote sensing data. So I want to remind you all that you can ask the questions in the Yopad, and then let's enjoy the talk.
Thanks a lot, Ivan, for the very kind introduction, and thanks a lot for inviting me to give this presentation. Thanks a lot, Stefan, for your talk and somehow that kind of follow-up discussion on the same topic on whether machine learning could fish data assimilation. I'm gonna give this presentation based on work with many colleagues in Brest, in France, mainly, presenting a specific approach based on this end-to-end idea that was mentioned by Stefan. So my focus is in terms of a playground. We rather play because we're close to the ocean in Brest, France. So my playground is more ocean forecasting or ocean reanalysis, but we really want to address question regarding how to solve sampling gaps, because for the ocean we have very sparse observations. As mentioned by Stefan, it's probably even more complex for the ocean in terms of observation sampling patterns. And we really see deep learning as a way to better bridge observations and modeling capacities to both for reanalysis and forecasting topics. So yeah, again, just as a follow-up of what was said by Stefan, when you consider possibly more for a machine learning point of view, the data assimilation pipeline, the goal is basically to use some observation data as input, and if you consider the reanalysis, the goal is to output some states, or that would be the same for forecasting, but for different space-time window. And the traditional way to design the data assimilation system is really to design each component of the system independently. So typically you have some physical model, you also design some observation model, and then you choose some kind of assimilation scheme, could be a variational scheme or some Kahneman approach. And then you combine all of these to design your system. But what's important here is that usually you optimize or you design each component of the system rather independently. So the key topic I'd like to discuss is whether trying to optimize the entire system as a whole could benefit in terms of a performance, because here the goal would really be to try to optimize the final some performance metrics regarding the state you'd like to reconstruct or forecast. So that was really what was mentioned by Stefan before. And in my case study, I consider the some sea surface observations and some sea surface state as an example that could be extended to possibly to other case studies. So there's quite some example of this in the literature, and I will present what we develop. And for sure, the first approach, which was mentioned by Stefan, is to use some state-of-the-art neural networks as a black box, let's say, and then to train, as mentioned for MetNet, to train the neural network based on some data. And there are also some kind of this kind of example for our case studies for the ocean. And possibly what I'd like to discuss more is how to design neural networks which can also leverage ideas of formulation classically used in data assimilation. So in our case, I will explore more variational formulation for data assimilation, but I also give you a reference here to a paper providing some kind of neural network-based reinterpretation of sequential data assimilation formulation, providing possibly some generalization in the same kind of end-to-end framework. I think what's also important is to see that there are many examples in the literature of neural network or machine learning approaches bridging neural networks and many different formulations used in physics. Could be ODs or PDs, could be Hamiltonian representation, many examples with Fourier operators. So somehow what I present here could be regarded as another illustration of this general approach of the ability to bridge machine learning physics in the case of variational representation to solve inverse problems. Okay, so the background here, I will briefly introduce variational data assimilation, because the way we design our neural scheme for our neural data assimilation scheme will be based on this variational data assimilation formulation. So basically, we use as a starting point a very classic state space formulation. So here X will be my state of interest. In my case, it would be some sea surface variable. And usually you send some physical model to describe the time evolution of the state. That's the first equation. And then you have some observation. Here I consider the simplest case where you basically observe your variable up to some noise at some location. And then one way to state the data assimilation problem, the reconstruction, and that would be the same for forecasting of the state, is to state this as the minimization of a variational cost, in which you have two main terms, some observation term, basically to state that the state you'd like to reconstruct should be close to the observation, should match the observation, and a second term here saying that your state should match the prior set by the dynamical model. And usually the operator for here refer to the time stepping operator of the dynamical model M in my first equation. So in the end, I can look to this formulation here, where using some kind of matrix form. So here X and Y are rather space-time volumes for the variable X and Y. And here you see that I can just rewrite it that way is in a simpler formulation, but still with those two terms. The first term, again, refers to the observation term, and the second one states some prior on the dynamics through this operator phi. And the goal, when you deploy variational data assimilation, you apply typically some kind of gradient-based solver to minimize this variational cost with respect to state X. And to implement this, you usually use some agile methods. So the goal here is very much the same. And we set two additional assumptions here. We assume that both the observation operator and the prior operator phi can be implemented as neural networks, meaning that they can be differentiated automatically. And then the idea is that we will define a solver, a minimizer for the variational cost, according to this update equation, where the plan is to iterate a number of gradient-based iteration, where at each iteration, you update the state according to a function of the gradient of a variational cost. What's important here is that you, instead of using a fixed step gradient descent here, you add some trainable operator, which is a specific class of neural network, which is a recurrent neural network. I may come back in details, but in our implementation, we use LSTM for those knowing this. So now what it means is, in the end, I can provide some kind of graphical representation of a neural network we will implement. So it will run a predefined number of iterations, let's say 10. And at iteration k+1, you use as input the current state at iteration k, and then you compute the gradient cost, you apply automatic differentiation to compute the gradient of reversional cost, then you provide this as input to the recurrent network, and then that will provide the mean to update the current state, and you iterate this a predefined number of iterations. That way, you get what we expect. It means that in the end, what you have is a neural network to which you can provide some observation data, and it should output some state, some reconstructed state. So in our case, the observation data would be sparse, so would be some kind of gap observation, and the output state would be a gap-free state. So now, because this is the box here is a neural network, you need to train some component, especially the R operator, which is the recurrent network. But in case you don't know some parameters or of the operator phi or of the observation operator, you could also learn during the training phase those operators in the variational cost. So there are different strategies depending on the available data set you can consider to optimize or to train your trainable components in the system. We can train, in the case you have simulation data, you have those kind of data sets for which you have your ground truth state, so the true state, the gap-free state, and you can also simulate the observation data set. So basically here, you can provide some to the system exact examples of the inputs and example of the output, and then you can directly train your system so that you get the best possible performance. We can also extend this to observation data. So basically here, instead of computing your performance metrics for all points, because you have gap-free state, you may compute this only for the observed observation. And a last option, you can, if you know all the operators in the variational cost, your training loss may directly be your variational cost. In that case, you truly learn the network to get the best possible optimization for variational cost. And you clearly see here that this is different from the first example I've provided, where the goal is truly to optimize the performance metric for the model. So this is the basic approach we develop. And here I provide you one illustration of its application to the reanalysis of sea surface height. So here it can be regarded as a space-time interpolation problem. So here it's for a simulation data set, meaning that we know the ground truth data, which is here. So it's some simulation using high resolution ocean model. And here you have the simulated data corresponding to realistic satellite observation patterns, either satellite telemetry combining both nadir along track data and Wadsworth data from SWAT. And as an illustration here, you have on the right, for the bottom right is reconstruction from the approach we propose, we refer to as 4D VARNet. And here you have illustration of the performance using some operation system which is based on optimal interpolation. So here you can probably see that you get a closer match between the neural network interpolation compared with the ground truth compared with the optimal interpolation. So obviously this is for a simulation data set. So you could say, okay, well, but does this generalize to real data? So here the very good news is that a model trained on simulation data can apply to real data. So here it's a comparison of the interpolation using 4D VARNet compared to two operational systems. So DUX is some kind of optimal interpolation approach, and GRORIS is some kind of model-based data simulation, which is an operational product. And the figures here refer to the resolved spatial scales of the interpolation. So basically here, what you see is that with 40 net, we can solve scales up to about 100 kilometers in terms of horizontal scales. And so with, like, let's say 50% of improvement compared to optimal interpolation, and a very significant improvement compared to the model-based data assimilation product. And interestingly, if you look here, that's here the sea surface height variable, and here it's the norm of the gradient of the sea surface height, which refers to sea surface currents to some extent. And I assume that you see that for optimal interpolation, we get a blurry gradient, and that the neural network gradient is more similar to the model-based data assimilation. Yeah, I don't know whether, okay, here. But what's important, so we get the same kind of patterns of the gradient using the neural network and the model-based data assimilation, but we get a better fit to the observation. And we get, somehow, it seems that the model-based data assimilation may be out of phase compared to the observation data. So here to me, it's some example for a 2D plus time case study that machine learning and your deep learning using some kind of data assimilation based neural network could outperform other types of data assimilation approach, because we have optimized and calibrated the system end to end to really optimize the interpolation performance. Okay, so we could also probably it's interesting to get insights on the performance of those 40 nets, those neural networks, depending on the way we set the prior in the model. So I haven't mentioned this, but before, but probably for the application to the sea surface height I've shown before, I haven't detailed much, but we need to choose some parameterization for the prior phi, which is the prior in the variational cost. And that should be designed as a neural network. So in the case you know your dynamical model, again, the operator phi is a neural integrator of the differential equation. So you could implement some kind of, for example, to be simple Euler integration scheme for your dynamical model. That would be one option. We can also use some kind of state-of-the-art neural network, for example, a UNet, as a way to represent the dynamics. Again, keep in mind here that X, in my case, is a space-time volume, okay? So meaning that the UNet here would input a space-time volume for variable X and output the same space-time volume. Here I provide an example, an illustration of the performance of the reanalysis for a toy model, which is a Lorentz 96 dynamics, using different types of parameterization of the prior in the 40 net. Those are the two solid lines. The cyan one refers to UNet, and this one here refers to the using the true ODE with some Runge-Kutta time integration. And here in this plot, I plot the evolution with respect to the number of iterations of the gradient solver of the reconstruction error on this axis. And here you have the variational cost. And we compare this to the dashed line here, refers to solving the variational cost using a fixed step gradient descent. What's important here is you see that you get the best score in terms of the minimizer of the variational cost using the fixed step gradient descent, because this is a goal. But if you look now at the performance in terms of reconstruction performance, you get the best performance using the UNet prior, and using the 40 net and using the UNet prior, meaning that we do not get the best performance in terms of reconstruction if we use the true ODE of the system. So that makes question that depending on the observation pattern you consider, you need to adapt the representation of the system. Okay, so yeah, so that was one example, and I've provided of this 4D VARNet framework. I've illustrated this basically for this. For sea surface height mapping, we have the same kind of illustration for forecasting. We have other illustration for other sea surface parameters, including for sea surface currents, which includes some non-observed component, meaning that we think that this kind of approach could also apply to non-observed variable beyond interpolation approaches. And what's also interesting, and I won't illustrate this today, is that it's, as mentioned by Stefan also, it's relatively straightforward to extend this approach to multimodal or inputs. So instead of using just one type of observation to get the best possible reconstruction or forecasting of the given state, we can consider different outputs and then adapt the variational representation to get additional terms in the variational representation to account for multimodal interaction between the observations and the state. So I won't describe this, but if interested, I could comment on this. I'd like to provide more additional insights on the extension of the 4D VARNet to account for uncertainty quantification, because in what I've presented up to now, what we are able to do is basically to get a deterministic reconstruction of forecasting from a given input. And for sure, we'd like to move to a probabilistic setting or to assess in some way the posterior, or to be able to sample the posterior. So we've explored different approaches for this. And I will shortly introduce the last one here, where the idea is to embed some kind of stochastic PD priors in the 4D VARNet approach I've presented before, and then to use this explicit SPD-based prior as a way to sample, and then to get this probabilistic approach. Okay. So the way it works here is that, again, because the starting point of the 4D VARNet approach is this variational formulation and the underlying state space formulation. So one idea which seems appealing to extend this to some kind of probabilistic approach is to take benefit from this underlying state space for formulation to make explicit a prior model, a prior on the dynamics, possibly in a stochastic setting, to get this probabilistic representation, and then to embed this in our 4D VARNet approach. So if we consider this kind of stochastic PDE, so relatively simple advection diffusion SPDE with some kind of fractional representation. So, but basically you can look into this as a relatively simple advection diffusion equation. So where X is as before just my physical state, but here I have additional parameters of the SPDD. Basically those parameters here, the advection terms, we have some diffusion here, and here you have a noise level. And the way we approach this, to use this, is that if you consider a space-time discretization of this prior, you can reformulate this PDE that way as a linear system with a matrix operator A of theta, where theta refers to all the parameters of the SPD. So again, the advection diffusion parameters typically. And what's important here is that because of the structure of the matrix A, we can get some explicit representation or computation of the inverse. So that provides the basis to to adapt the variational representation I've introduced before. And basically, it's based on just a re-parameterization of the operator phi, or specific parameterization of operator phi, which relates to the above mentioned matrix formulation A according to this parameterization. So you see here that the parameterization operator phi is relatively simple. It's just a linear model. And then what's interesting is that we can apply relatively straightforwardly the Fordy-Varnet framework. The very simple idea is that instead of applying the Fordy-Varnet only to the physical state X, we consider some kind of augmented state combining the physical variable X and all the parameters of the SPDE. And then we can define the variational cost based on the SPDE prior. And we can also adapt the training loss to account explicitly for the SPDE prior. And then based on this, we can directly apply the Fordy-Varnet scheme I've presented before. So all this will remain just the same, but the only difference here is that the X is no more only the physical state, but combines the physical state and the parameters of the SPDE. And then we adapt the parameterization for operator phi. But the recurrent network for the trainable solver is exactly the same. Here I provide you, those are very preliminary results, so I just provide you some preliminary results here. And the first result here is that what's very interesting is that we get the same performance, or very much the same performance using this SPDE prior as the performance we get for the Fordy-Varnet using the UNet prior I've mentioned before. So meaning that here, that using either we use the SPDE or the UNet prior, we get the same performance. So those two models have somehow the same ability in terms of optimizing the interpolation performance. But what we gain from the SPDE is that we get this additional ability to sample the posterior. So we can sample realization of a state conditionally to the observation. And the reason for this is that if we have some estimation of the parameter theta, we can get some simulation of the state X just according to this linear mapping between the noise Z, which is just a realization of the Gaussian noise, and multiply by that's more the matrix A I mentioned before. So something
just 4 minutes left, please.
Okay, perfect. Sorry, yeah, I was in. Oh, sorry. Okay. Okay, so I was here. So, and you may see here, it's relatively small, but here you have example of different realization of the sampling. So, and it seems we need to investigate this further, but it seems that we get something relatively realistic in the kind of uncertainty or sampling of the posterior intent with structures which seems relevant in terms of ocean sea surface dynamics. But we need to investigate this further for sure. So here maybe a number of take-home messages from this talk. So I hope I've provided you one example, or ready to push forward the discussion initiated by Stefan, that on our side we think that it's really worth investigating like end-to-end learning ideas for neural data assimilation, and that we can also bridge this to generative models, as illustrated by this last example combining Fordy-Varnet and SPDE. Somehow, and as mentioned by Stefan, again, the goal really of end-to-end learning is really to optimize your entire system according to some performance metrics, and possibly the performance metrics should like referring to the application you consider. So That's very much the case in the interpolation problem. But if that's true that you can train a system according to your preferred performance metrics, you can really expect to get a breakthrough, as mentioned by Stefan. And then you also get this some kind of user-centric or end-to-end standpoints, which may be relevant. I also think that this, what I've presented before, illustrates some new means to build models and some observations. So again, using, in our case, as mentioned for the application to sea surface height, we train our neural network end-to-end from simulation data set. So meaning that we use high resolution simulation from ocean models, and we also use some simulation of the observing systems that provide a fully simulated training data set from which we can train neural networks, and then we can apply those models directly to real observations. So that provide new ways then to possibly some alternatives to training models from reanalysis data purely. Another important point that all this has been possible through the setting up some kind of collaborative, reproducible research framework, very much inspired from Weatherbench, and we've recently presented a paper on NORIT this year, referred to as Ocean Bench, trying to implement the same kind of framework as Weatherbench, but for ocean problems, and with a first edition referring mainly to sea surface height, interpolation, reanalysis, and forecasting. And the last point I'd like to mention is that the gain, I really see a gain with this shift to AI native framework. Again, because you have this both in the computational efficiency, because you can use GPUs, but also through this all-purpose differentiable programming, you can really optimize any component of your system. And to me, that's a very, very strong benefit and a very strong bottleneck of approaches trying to improve current systems for which you don't have this the differentiability of the different components of the system. So we really want to move forward into this direction of developing end-to-end systems, both for modeling, forecasting, and data simulation, with this focus on ocean case studies. So this is it for me. Here I just provide a number of papers if you'd like to know more. And I've mentioned, but we also have a number of works not mentioned today, but on closures for solvers or for geophysical dynamics, with the same illustration of the potential breakthrough associated with end-to-end learning. That's it. Thanks for your attention, and I'll be pleased to answer questions.
Okay, thank you, Ronan, for this interesting talk. So let's switch to the questions. So here's one. Roughly how much overhead in memory and computation compared to the nonlinear forecast model is the automatic differentials adjoint during the gradient cost?
Okay, yeah, it's for sure. So it really depends. The memory cost of the differentiation of the variational cost really depends on the structure of the different operators, and especially of the representation of the prior. So meaning that if you implement some kind of solver of a PDE, for example, the computational or the memory cost would be higher probably than applying a UNet prior, for example. And that's that's a constraint in this approach currently, or that's one requirement. So but we run this maybe in terms of computational complexity we can run. We run this on basically for domains of a few hundreds by a few hundreds by a few tens of days in the training mode. So for and then so yeah, as a typical complexity. And we, for example, for GPUs with about 40 gigas of memories, that's the typical setting. But for example, if you would like to run this for grids of thousands by thousands, that won't be possible or we do much larger GPUs in terms of memory. So I would expect that if you have this, a solver for a PD, that would be even much higher.
Okay, thank you. So then another question by Drew Peterson. He's worried that he's not understanding. So were all the examples presented for 4D VAR net targeting a single observable? And then he further explains reanalysis have to fit many observables. So is the comparison fair?
Yeah, I understand this. Okay, so we have here that's an illustration. The illustration for interpretation, that's for true. We just consider the sea surface height, so one observable and one which is directly observed. So you may consider that the comparison to an operational data assimilation system is not fully fair, and I agree with this. But we also have, so we're looking for extension or demonstration for beyond a single observable. And currently we have some additional, I'm looking for this. Yeah, so probably here. We have examples for which we can consider several observation inputs, but we still optimize the system for one output. And the question might be whether if you want to also get reanalysis for many observables, whether it's better to solve everything at once, or whether it might be better to solve this in a blockwise way. I mean, observable by observables or groups of observables by groups of observables, which might be possible with learning techniques.
Okay, thank you. There's still some questions left in the YoPad, so Ronan, please answer them if you have the time afterwards.
Sure.
And then I'd like to hand over to Lars, I think, for your concluding remarks.